We're back with another example that comes out of algebra, and that is rational expressions. We typically kind of go, and this is going to kind of go along with what I just did. Frequently I hear, how would I ever use this? And again, this is going to come down to helping us with things that involve, for example, area. Okay? Now, what I mean by a rational expression, let's go to the board here, something of this form. You've got some kind of polynomial on the top, you've got some kind of polynomial on the bottom. We call the top part the numerator. This is grade school stuff. The bottom is the denominator. But when we go to these things, there is a complication. We have to be sure that we don't plug in values of x into the denominator that will make it 0. Okay? If we look at the graph of things like this, or we think about this expression, and we look at the graph of it, we said y equals this thing, that's going to be the location of a vertical asymptote if it also makes the numerator something other than 0. If they're both 0, if the denominator is 0 and the numerator is 0, then the graph is going to have a hole in it, and that's a hole that won't show up in most cases when you graph things. And let me just quickly jump out of here. I want to show you very quickly some of the kind of things that can pop up with this. Let's see, is that the one I really want? Yeah, no. Sorry, I'm fumbling around with the stuff. I tell you what, before I show you this one, let me show you, go right here and I'll get it. Segment 2, 3, here we go. Sorry for the fumbling around. Something like this is a perfect example of a polynomial kind of in the top, polynomial in the bottom. And I want to point out to you what these things mean. Now right now I've got everything zeroed out, so this is 0. That's this big blue, purple line across the bottom. But as I perhaps let this b be a positive number, watch what happens. You can see here we've got a vertical asymptote right here when x is equal to 0. And then I can move that around when I change c. That asymptote moves left and right. So that's really what the c controls. And then the a would control up and down kind of changes. Okay? And that little dotted line you see is the horizontal asymptote that's going on. Okay? The other thing is, what if I go to a square? Sorry, let me do this a little better. If this is an ax squared up here, the change is about the same. The c is going to, again, oh wait, let me make this. You get that same kind of shape, and the c moves it left and right. We talked about this. But because the power of this is higher than the power of that, you don't end up with a horizontal asymptote. You end up with a kind of a slant. Watch what happens when I tilt this a around. Okay? Now how that's useful to us is it has, the way things are drawn now, if I just look at the positive things, I actually have a minimum here. And this is the kind of thing that your calculator can find for you. It's also the kind of thing we can find with calculus, but now calculus is a little bit above what we're going to be talking about. If I want exact answers, I have to use calculus. If I'm willing to settle for approximate answers, I can just go with the calculator and let it tell me the answer. So let's go back then to this kind of stuff. And I do want to say just very quickly, this whole business of dividing by 0, why can't you do it? You know, this is something we all take for granted, but probably nobody's ever explained it to you. What we mean when we say a divided by b is c, it means that a is equal to b times c, and that c is a unique value. So if b is 0, and that's what we're talking about, dividing by 0, that turns into A equals 0 times C. And if A is not 0, we got a problem because it has to be 0. If we let A be 0, however, then I get 0 equals 0 times C. And the C can be anything. It's not unique. So because it doesn't fit the way we define division, we say it is undefined. Okay, I don't know if anybody ever explained that to you or not. I felt like I owed it to you to explain why we leave that 0 out of the denominator. All right, let's go to an example. I want to go back and look at that problem I worked before, actually, with the farmer wanting to enclose the rectangular area. And we made the assumption when we worked that problem that we were going to use all the fencing we had, the 100 feet length of fencing. But I was only trying to enclose 600 square feet. So the question, a good question would be, could I get by with less fencing material? Okay, in fact, what would be the minimal amount of fencing I would need to enclose an area of 600 square feet? I know I can do it with 100. Can I do it with less? Okay, and how does this involve rational things in the first place? Well, now I've kind of switched things out. I'm fixing the area. So the width times the length would be 600. And now the perimeter can change. Okay, the only constraint I really have is that I have to use less than 100 feet. I mean, I'm not, I know that's less than 100 feet because I've already worked that problem. Okay, that does mean still that the width it's going to range between 0 and 25. 25 would be a square, right? 25, 25, 25, 25 gives me 100. But now I've got the two equations, two unknowns. I want to solve for one of the unknowns. The one I will solve for is the length. I'm dividing by the width. Now that means I can no longer use 0 as an answer. It's a subtlety, but it's a fact that I now want to avoid that answer 0. And I'll do what I did last time, and that is jam it into the other equation, which you can clean up a little bit. This is an equation now that involves rational expressions, and that's what we're talking about. And this is how I would use it. To solve this, and you can clean up a little bit, fine. To solve this without calculus, I would go to my graphing calculator. I would draw that curve. Can I do this in less than 100 feet perimeter? Yes, I can. And I could tell you exactly if those lines cross again at 20, okay? But if I want the minimum, I use the functions on my calculator and find that to be about 24.5 feet, okay? Which is roughly, it turns out that's roughly square root of 600. That's actually the exact answer. If you use calculus, that's the exact answer, which means that the length would also be the square root of 600, and you end up with a square. Okay? Cute little example of how rational expressions, right now you're just playing with them, you're not solving equations, but here's exactly the way they're going to be used later on when you actually start getting down to the nitty-gritty of solving for distances and stuff involving area. And I'll just quickly flash up some of the things that I talked about for you to kind of look at. We're at the end of another episode of Math Matters. I hope you enjoyed the examples I showed you today. I realize I moved a little fast through some of those, so let me remind you that all the stuff you've seen here today, the segments we've produced, are located on the Math Matters webpage, and we'll flash up that address here at the end of the program. Take advantage of these things. I think hopefully you will find it helpful as you proceed through your classes. Also, let me remind you that I'm always looking for great examples or suggestions for improving the show. So make sure and use that email address and contact me if I can be of any help to you. We'll call it a day then. Thanks a lot for tuning in. I'll see you next week.